All right, let's talk about building a professional regression model. It can seem like this huge, complicated thing, but we're going to break it down into a really straightforward, structured journey. So let's just dive right in.
So here's the big question, right? You start with this raw, messy pile of data, and somehow you're supposed to turn that into a reliable model that can actually make accurate predictions. How on earth do you get from point A to point B? Well, I'll tell you, it's not magic. It's all about having a systematic workflow.
The best way to wrap your head around this whole process is to think of it like a journey that happens in 3 distinct phases. And along the way, you're actually going to put on 5 different hats, play 5 different roles. Mastering each of these roles is really the key to building a model that's not just powerful, but one you can actually trust.
So here's our game plan. First up, we're going to be the detective and the chef. That's all about the data. Then we'll switch hats and become the engineer and the doctor to build and diagnose our model. And to wrap it all up, we'll step into the role of the final decision maker to choose the absolute best path forward.
Okay, let's kick things off with phase 1. Look, before you even think about building a model, you have to get to know your data. I mean, really know it. And that's where you step into your first 2 roles, the detective and the chef. So your very first job is to put on your detective hat. This is what we call exploratory data analysis, or EDA for short. You're not building a thing yet. You're just investigating, snooping around. You're on the hunt for patterns, weird anomalies, interesting relationships, any clue you can find that tells you what story the data is trying to tell.
So what's in a good data detective's toolkit, anyway? I mean, how do we actually do this investigation and find those critical clues? Well, there are a few go-to tools that we always rely on.
And here are the big 3. First, you've got your histograms and box plots. These are great for looking at one variable at a time. You're asking, what's its shape? Is it skewed way off to one side? Are there any crazy outliers? Then, the scatter plot is your best friend for checking the relationship between one of your features and the thing you're trying to predict. You can literally just see, is there a straight line connection there? And finally, you run your descriptive stats. This just gives you that quick and dirty numerical summary, the mean, the median, and crucially, a count of any missing values.
Okay, detective work is done. You've got a full report on your data's quirks and features. Now it's time to switch hats. You hang up the trench coat and you put on the chef's whites. A chef's job is to take all those raw ingredients, your data, and based on what the detective found, clean them up, prep them, and turn them into the perfect dish, all ready for modeling.
But hold on. Before our chef even picks up a knife, there is one absolutely critical rule they must never, ever break. And that is avoiding data leakage. This is a huge, huge mistake. It happens when information that you won't actually have when you make a prediction accidentally sneaks into your training data. It'll make your model look like a genius during development, but it will fall flat on its face in the real world. So with that warning in mind, the chef's recipe has 4 basic steps. First, you get rid of any of those cheating features to prevent leakage. Second, you deal with any missing data. Filling in the gaps with the mean or median is a common trick. Third, you might transform some features, maybe using a log transformation to tame some really skewed data. And finally, because models only understand numbers, you've got to encode any text categories using something like one-hot encoding.
All right, our data is prepped, clean, and ready to go. So let's move on to phase 2, where we finally get to build and then diagnose our model. This is where you'll be playing the roles of the practical engineer and the analytical doctor.
As the engineer, your first job isn't to go build some crazy, complicated supermodel. Nope. Your job is to build a simple, reliable baseline, something like a linear regression. This thing is so important. It's not just a starting point, it's a reality check. It proves your problem is even solvable before you go and waste time on more complex stuff.
So, once your baseline model is engineered, it's time for the next role change. You are now the doctor. And your patient? It's the model you just built. Your job is to give it a complete top-to-bottom health examination. We need to find out if it's not just accurate, but if it's actually healthy.
So, what's the first thing any doctor asks? How's it performing, right? For us, that means accuracy. How good is our model at predicting the outcome? Is it even in the ballpark? We need some numbers, some metrics to tell us. For this, we've got 2 key metrics, MAE and RMSE. MAE, or mean absolute error, is pretty simple. It tells you, on average, how far off your predictions are. RMSE, or root mean squared error, is similar, but it punishes big mistakes way more harshly because it squares the errors. But here's the real magic. It's when you compare them. If your RMSE number is way bigger than your MAE, that's a huge red flag that your model is making a few really big mistakes, probably because of some outliers. But look,
Just like in medicine, good numbers on one test don't tell the whole story. A model can be accurate on average, but still be fundamentally broken on the inside. So the doctor's next question goes a lot deeper. Beyond just its accuracy, is this model actually healthy? Can we trust it? And for that, we need the doctor's advanced diagnostic toolkit. The residuals plot. Think of it like an EKG for your model. It's the best way to just see if the model's basic assumptions are holding up. Cook's distance is like checking a vital sign. It tells you if there are any single data points that are having a massive, unhealthy influence on the whole model. And for a linear model, you have to check the coefficients. They tell you exactly how each feature is affecting the final outcome.
We've made it. We're at our final phase. We've got the full diagnostic report from the doctor, and now it's time to use that information to refine our approach and pick a winner. It is time to become the final decision maker.
This is really where it all comes together. I mean, you've been a detective, a chef, an engineer, and a doctor. Now you have to take everything you've learned and make a smart, strategic choice. The doctor's report doesn't just give you the answer. It gives you the evidence you need to decide what to do next.
So based on that health report, you basically have two main paths you can take. Path one is to iterate. If the report showed some problems, maybe you go back to being the chef, try a new feature transformation, and then rerun the whole process. Or there's path two, upgrade. If your simple model just isn't cutting it, maybe it's time to bring in a more powerful tool, like a decision forest model.
So let's imagine we actually did both. We went back and improved our linear model, and we also built a brand new, more complex decision forest. Now comes the moment of truth. It's time for the final showdown. We have to compare these two models head-to-head and officially declare a winner.
And this table just lays out the classic trade-off perfectly. I mean, look, Model B, the decision forest, is the clear winner on accuracy. It's got a higher R-squared and a lower error, or RMSE, no question. But then you look at the other stuff. Model A, our simple linear regression, is way easier to understand and a lot cheaper to run. So, which one's better?
And that really gets to the single most important lesson here. There is no such thing as the best model in a vacuum. The best model is the one that actually solves the business problem. If you need to be able to explain why a prediction is being made, well, that highly interpretable Model A might be the right call, even if it's less accurate. But if all you care about is raw predictive power, then Model B is your champ. It's always a strategic decision.
And that's our workflow. But you know, it's so important to remember that building a model, that's not the real finish line. The real goal is to take that model and use it to create actual value in the real world. So really, the end of this workflow is just the beginning of your model's story. Now the question is, what problem are you going to solve with yours?